Hello and welcome everyone. My name is Sandeep Sani, M.Sc Applied Geology from Indian Institute of Technology, Roorkee. Today I am presenting a seminar on folds and folding and its basic concept. This presentation is being delivered under the guidance of Dr. Sandeep Bhatt, Assistant Professor at IIT Roorkee. In this video, we will explore the concept, classification and terminologies of the fold. And this is my flow of presentation where we start with introduction, basic terminology of fold and its classification. Now I am going to start with the basic definition of fold. What is fold? The fold is a wave-like structure that forms due to the bending and flexuring of rock layers. These layers can belong to igneous, metamorphic and sedimentary rocks. The word fold was used by Hole 1815 for the first time to explain the rock structure. The folds can be a various size range from microscopic to megascopic. The fold may be single layer or multiple layer. This is the photo that shows how fold look like in the field. Let's understand the terminology used to describe the fold. First we describe the hinge point. The point of maximum curvature of fold layer is located at the center of the hinge zone and it's called the hinge point. This is the hinge point that shows the maximum curvature. And next we have a hinge line, a line joining a hinge point located at the maximum curvature in 3 dimensions. It's a curve or stretch. This is the hinge line. Next we have a fold axis. It is an imaginary line on a fold surface which when moved parallel to itself generate the fold surface. In continuing with fold terminology, we have a crest point located at maximum height with fold layer with reference to the horizontal reference plane. Next we have a trough point, a point located at a minimum height with reference horizontal reference plane. Next we have a inflection point, a point of zero curvature. At this point the sense of curvature changes. From here the curvature of the fold will changes. Next we have a limb. Limb is a portion of fold between the hinge line and the inflection point. Each fold has 2 limbs. These can be symmetrical or asymmetrical depending on the fold type. Next we have interlimb angle, the angle between the 2 tangents drawn at the inflection point of the fold. Next we have an inflection surface, a surface joining successive inflection lines in different layers within a single fold. Next we have a axial trace. The axial trace of a fold is the line of interaction of the axial surface with the surface of observation, typically the surface of an outcrop or geological section. Then we have a axial trend. It is the azimuth of a hinge line. Then we have axial surface. It's an imaginary surface joining multiple hinge lines in a single fold affecting various layers. This is the axial surface. Now let's talk about the fold classification. We classify the fold on the basis of different things that are listed below. First we classified the fold on the basis of its symmetry. Then we classified the fold on the basis of its closure based on the stratigraphy. Then basis of the fold orientation. Then we classified the fold on the basis of fold tightness based on hinge type. And last we classified the fold on the basis of M.Sc classification. In this slide, we classified the fold on the basis of its symmetry. Here the two types of fold on the basis of symmetry: symmetric fold and asymmetric fold. Asymmetric fold. Fold is symmetric if in a profile the shape of one side of length of the hinge is mirror image on the other side and the limbs are identical in length as shown in the figure. If we look around the axial plane, the length and the shape of the limbs is identical and mirror image the length and shape of the other side. This is known as symmetrical fold. An asymmetrical fold, a fold that does not have any mirror plane of symmetry in the limbs are the unequal length as shown in this figure. This is known as asymmetrical fold. Next, if we have multi-layer folds, then we have to classify the fold on the basis of symmetry in harmonic folds and disharmonic folds. The harmonic folds in which the axial plane are continuous across the successive fold layers that show approximately the same wavelength and amplitudes are known as harmonic folds as shown in figure. And disharmonic folds, the folds in which the amplitude, wavelength and style change along the discontinuous axial surface from the one layer to another, known as disharmonic fold. As shown in this figure, the first layer have a high amplitude where the another layer have a low amplitude, and along this axial surface we have different amplitude and wavelength of the different layers. That's known as it's a disharmonic fold. Next, we classify the fold on the basis of fold closure. In this way, have three types of folds. Antiforms. An antiform is a structure where the limbs dips downward away from the hinge zone. As shown in figure, if we look the figure, the limbs are dipping away from the center. This is known as the antiform. And next we have synform. And synform is a structure where the limbs dip down and toward the hinge zone. As shown in the figure, as we look at the figure, the limbs are dipping toward the core of the fold and hinge. This is known as synform. Then we again a fold which is known as a neutral fold, a fold which close laterally and is therefore neither antiform nor a synform. This is a neutral fold. Here we classified the fold on the basis of stratigraphy. Means if we include the age of strata in classified the fold, then we classified the fold in two types: anticline and antiform. Anticline and antiform is called an anticline where the oldest rock exposed in the core of the fold. As in this figure, if we have oldest rock in the core of the fold, then this type of fold known as an anticline. Next we have syncline, and the syncline form is called syncline where the youngest rock are found in the core. Means if we have a younger rock in the core and compared to the outer, then we call this type of fold known as syncline. And we have two different forms: antiformal syncline and synformal anticline. Means if we have a form as an anticline and the younger strata in the core, then it's known as an antiformal syncline. And if have a syncline form and the older rock in the core, then this known as a synformal anticline form. Now let's move on an important classification scheme used in structural geology: the classification of fold based on the fold orientation. This classification helps us to understand how folds are positioned in three-dimensional space by looking at the critical components, the orientation of hinge line and the axial surfaces. This classification developed by the Floaty 1964. In this diagram, as we shown as the vertical axis show the plunge of the hinge line. When we move from top to down, the plunge of the hinge line increases, and the horizontal axis we have the dip of the axial surface. This is describe how much the axial plane is inclined. Its range from 90 degree to the 0 degree horizontal from left to right. Now let's go through the each fold that's shown in this figure. First we have an upright fold. These folds have a vertical axial surface with 0 plunging, and then we have plunging upright fold. Similar to the upright fold, but here the hinge line is plunged into the ground. It means the hinge line at an angle with the horizontal. Now we have a vertical fold. In this, the plunge is around 90 degree, and the axial surface is again a vertical, and this is known as vertical fold. When we move from left to right, we have inclined fold. This occurs when both hinge line and axial fold are inclined. When the hinge plunge and axial surface is inclined, we get plunging inclined fold. And with special types of fold, this is known as reclined fold. These are formed when both the hinge line and axial plunge in the same direction at low angle. The axial surface is gently inclined and the hinge line is nearly parallel to it. Then we have again recommend fold. This is the extreme case where the axial surface is nearly horizontal and the hinge line also nearly horizontal. This type of fold known as a recommend fold. Now let's look at the classification of fold based on their orientation, especially using stereographic projection. These diagrams help us to visualize the orientation of fold axis and axial plane in 3 dimensions. This classification based on the orientation of both hinge line and axial plane. Here we have upright fold. This is the upright fold where the axial plane is vertical and the hinge line is horizontal. If we plot the upright fold on the stereographic projection, then we can see a great circle represent a vertical axial plane as a straight line passing through the center, and the fold axis is plotted at the point lying at the horizontal. As we talk about the vertical fold, in a vertical fold, both axial plane and the hinge line are vertical. On the stereo net, the fold axis appears near the center and indicating a vertical plunge. In the recommend fold, here we have a recommend fold. The axial plane is nearly horizontal and his line also is horizontal. That's why we have a dotted line at a circle, great circle. Then we have an inclined horizontal fold. In this an inclined fold with a horizontal hinge line, the axial plane is moderately inclined and the hinge line remains horizontal. The stereo net reflects this with a moderately inclined great circle and the point at the edge of the horizontal fold axis. This is known as inclined. Like that, if we have a reclined fold, and this is where the axial plane is inclined and the hinge line plunging same in the direction of axial plane. The fold axis lies along the great circle, indicating both are aligned in the same direction. Fold can also be classified on how tightly the limbs are bent. This is known as fold tight classification. Here we have gentle fold, open fold, close fold, tight fold, and isoclinical fold. The gentle fold has an interlimb angle around 180 to 120 degree. In an open fold, we have interlimb around 120 to 70 degree. In a closed fold, we have 70 to 30 degree, and in tight fold, less than 30 degree. And in isoclinic fold, the limbs are parallel. This is diagram show how the tightness of fold are shown in a outcrop in a profile section. Now let's classify fold based on the shape and structure of the hinge line. We classified the fold on the shape of the hinge line. There are two types of fold: cylindrical fold and non-cylindrical fold. A cylindrical fold has a straight hinge line, which means the fold can be generated by moving this line parallel to itself. These are common in simple linear structures. A non-cylindrical fold has a curved or irregular hinge lines. Then we have more complex forms. A dome is rounded antiform where the hinge line culminate upward. Rocks dip away from the center of the high point. And another type we have basin. This is the opposite of the dome. Rock dip inward, a center low point forming a synformal structure. Then we have saddle in an antiform where the hinge line curves downward, giving a saddle-like appearance. Here is a dome. The hinge line is like that. And in basin type, the rocks dip toward the center and the low point, forming a synformal structure. This is type of saddle. Now, moving into one of the most advanced fold classification system, geometrical classification, given by John G. Ramsey, introduced in 1967. This classification is based on dip isogon, orthogonal thickness, and axial plane thickness. The dip isogon lines join point of equal dips on the either side of fold layers. Then we have orthogonal thickness at the distance between two tangents at the outer surface and inner surface. This is the orthogonal thickness. Then we have axial plane thickness. It interprets between the two tangents of the line parallel to axial surface trace of the profile plane. This is the axial plane thickness. This is measured at the hinge of the fold. In this classification, we take a ratio between orthogonal thickness at the angle to the orthogonal thickness at the hinge. We take a ratio of T naught T alpha upon T naught as shown in figure. The geometrical classification fold by Ramsey. Ramsey classified the fold in three classes: class 1 fold, class 2 fold, and class 3 fold. In class 1 fold, the dip isogon converges, meaning the outer arc has a larger radius than the inner arc. The class 1 fold are again classified into three classes: class 1A fold, class 1B fold, and class 1C fold. In class 1 fold, 1A fold, the fold has minimum orthogonal thickness at the hinge. This means they are the tightly curved at the center, originally known as supertenuous fold. In class B fold, in which the orthogonal thickness is constant along the layers, means T alpha is equals to 1, which means these are the parallel fold. And in class 3 fold, in that orthogonal thickness is maximum at the fold hinge and decrease away from it, as shown figure. This is known as class C fold. Then we have class 2 fold with dip isogone parallel to axial plane, also have a identical inner and outer arc. This is known as a parallel fold. In class 3 fold, we have a diverging dip isogones with a higher curvature in the outer arc compared to the inner curvature. This creates a pinch core and is often associated with the intense deformation zone. Then we have miscellaneous folds. In this we have Severan folds. Severan folds are sharp, angular folds with straight limbs and narrow pointed hinge. They often form in rock with their strong planar fabrics. Concentric folds. The fold surface defines circular arc with common center. As shown in figure, this is a concentric fold which is have a common center and a concentric circular arc. In a box fold, the crest is broad and flat. Two hinges are present on the either side of flat crest. As shown in the figure, we have two hinge lines in a box fold and the crest have a flat. This type of fold known as a box fold. Here we have two types of folds, pygmatic folds and parasitic fold. Pygmatic folds are irregular lobate fold usually found where the single competent layers are enclosed in a matrix of low competent layers. Here's the diagram show the pygmatic folds. Then we have parasitic folds. Parasitic folds are the smaller folds that occur within the limbs of larger primary fold. We refer to the large structure as a first order fold and the smaller associated one as a second order fold. As shown in the figure, we have a large fold and in this we have a small parasitic folds within the limbs of the larger folds. This is known as parasitic fold. In previous slide, we discussed about parasitic fold. Now we discuss about anticlinorium and synclinorium. Anticlinorium is a large anticlines of which minor folds are superimposed, and a synclinorium is a large syncline on which minor folds are superimposed. In this anticlinorium and synclinorium, we have different small fold types known as M fold, typically symmetrical and upright, representing the anticline of the cross section. Here, this is a M fold, this is the anticline fold. And W fold, symmetrical and upright, representing a syncline. This is known as a W fold, which is found at the trough of the fold, large folds. And we have a Z fold. All parasitic folds in a limbs have a clockwise apparent vergence, and the described as a Z fold. This is known as Z fold, clockwise vergence. If we define as a Z fold, a large limb with smaller and then large, this make a shape of Z. That's known as its Z shape. In another side of limbs, we have large limb, then smaller, and then large. This form a S type. Then this is called as a S fold. Next, we discuss two critical concepts: facing and vergence. Vergence is the apparent direction of fold symmetry. When viewed in cross section, it tells us about how the upper part of fold has shifted relative to lower part, as shown in figure. Here we can see how the upper part of fold is shifted in compared to lower part. This is known as vergence. And facing refer to the direction in which the younger beds or statical ringing orientation of the fold. As shown in figure, as we have fold and the younging direct, the facing always directed toward the younging direction of fold. These are the references that I took for making this PPT. Hope you will understand. Thank you.